Hello friends, welcome to another video on parallel RLC circuit analysis. So don't forget to like, subscribe and comment. Your comments are basically very important for me in order to improve the quality of the video. So let us discuss this thing. So parallel RLC circuit contains R, L and C in parallel. All these three are connected across the supply voltage. So look, Is is the current which is flowing. This is the main current getting divided into three parts: IR, IL, and IC. So Is is going to be the vector sum of all these three currents. So let us see how this analysis goes on. RLC circuit. Here is the phasor diagram. IC is the current through this capacitor. IR is the current through this resistor, and IR is in phase with V. As we have seen that resistance, current through the resistance is in phase with voltage. But the current in the capacitor is 90-degree leading. So here it has been shown 90-degree leading. Whereas the current in the inductor is 90-degree lagging. So that has been shown lagging here. Now, in order to arrive to the conclusion that how the vector sum is calculated, you have to take the difference. This is IL minus IC. So this is the difference of IL and IC, and this is IR. So when you draw the diagonal of this parallelogram gives you the value of Is. This is nothing but the resultant of these two currents. On one side, it is difference of the current, IL minus IC, and on the other side, it is IR. So this diagonal is the resultant of these two vectors, IR and IL minus C. And the these vectors are rotating vectors. So the direction of rotation is always anti-clockwise, as shown here. So the total current Is square will be equal to IR square plus IL minus IC to the whole square as per this triangle. This relationship is like this, right? So Is becomes a square root of IR square plus IL minus IC to the whole square. Now if you substitute the value of IR, which is equal to V upon R to the whole square, uh, within the bracket V by XL minus V by XC to the whole square. So if you calculate this thing, you will get V upon Z. V upon Z. But how? IR is equal to V upon R, IL is V upon XL, IC is V upon XC. Okay, so if you take V square common and you take it out, rest of the thing will aggregate to Z. So that is why it has been written directly V upon Z. Right? Now according to KCL, Kirchhoff's current law, Is minus IR minus IL minus IC within the loop, these three currents are being caused by Is. So the sum of all these three currents will be equal to 0. So Is minus V upon R minus 1 upon integration of V dt minus C dV by dt will be equal to 0. So Is minus d2v, uh, just a minute, Is minus d2v dt square dt2 minus dv by rc dt minus v by lc will be 0, and this will end up with ist is equal to instantaneous value d2 v by dt square plus dv by dt into 1 upon rc plus 1 upon lc p. So the opposition of the current in this type of AC circuit, that is parallel circuit, is made up of three components: XL, XC, and R. With the combination of these three values giving the circuit impedance Z, we know that the above voltage has the same amplitude and the phase in all the components of the parallel RLC circuit. And then the impedance across same voltage is getting applied to all these three elements. V is the voltage. So impedance of the parallel RLC circuit R equal to V upon IR, XL V upon IL, XC V upon IC. Z is equal to 1 upon square root of 1 by R plus 1 by XL minus 1 by XC. Okay, so 1 upon Z will be what? This much of thing. So 1 upon Z is what? 1 upon Z is called admittance, and the symbol is Y. So this whole thing ends up to be 1 upon ZT equal to YT is equal to Y1 plus Y2 plus Y3 plus. So admittance of the parallel circuit can be calculated in this manner. Okay, the parallel circuit has been shown here. Okay, so y1 is equal to 1 upon z1, y2 equal to 1 upon z2, y3 equal to. So this is the generalized picture of the parallel circuit, as here the impedance, total impedance or the inverse of the impedance can be calculated in this circuit by having the, admittance of this circuit and this circuit separately and summing them up. So that is what it is showing in this calculation. The unit of measurement of the commonly used admittance is Siemens. This is very noteworthy that this admittance is measured in Siemens and it is abbreviated as S. Symbolically, it is written as S. So this is the unit of, other unit is, old unit is mho, which is reverse of OHM, ohm. Okay, this is reverse of ohm. So the word ohm had been reversed to measure it. Ohm's reverse. Admittance are added together in parallel branches where impedance are added together in series branches. This is the difference between series and the parallel circuits. So in the parallel circuit, admittances are, different admittances are added, whereas impedances are added in the series circuit. This is the difference. But we can have the reciprocal of impedance. We can also have the reciprocal of resistance, reactance, and impedance consisting of R and X. And then the reciprocal of resistance is conductance. Reciprocal of reactance is susceptance. Earlier also this has been discussed in the earlier videos. So you can see the other videos also. Conductance, admittance, and susceptance. So conductance is the measure of how nicely a conductor will conduct. All right. Admittance is the reciprocal of impedance and is given by Y. In AC circuit, admittance is defined as the ease at which the circuit composed of the resistances and reactances allows the current to flow. Ease with which the current will be allowed to flow in the circuit having resistance or reactances. Resistance and reactances or reactance when the voltage is applied. The admittance of the parallel circuit is the ratio of the phasor current and the phasor voltage, with the angle of admittance being negative to the impedance. So Y equal to 1 upon Z Siemens. Conductance is G and 1 upon R Siemens. Susceptance BL is 1 upon XL Siemens. BC is 1 upon XC Siemens. Okay, BC is capacitive uh, susceptance and XC is capacitive reactance. BL is inductive susceptance and XL is inductive reactance. So the reciprocal of reactances are measured in Siemens. That means susceptances are measured in Siemens. We can therefore define the conductive and capacitive susceptance as being BL equal to B at an angle of minus 90 degree. And it can also be written as 0 minus JB. BC is equal to B at an angle of plus 90 degree, and it can be written as 0 plus JB. In AC series circuits, the position of the current flow is impedance Z, which has two components R and X. These two components can construct the impedance triangle, and similarly in parallel RLC circuit, admittance Y has two components. One is conductance represented by G, and the other is susceptance represented by B. And this makes the triangle to construct admittance triangle, like we had impedance triangle. Here we will call it admittance triangle. And admittance triangle is shown here in the picture. The impedance triangle is on the left side and admittance triangle is on the right side. So you can see these two triangles. Admittance triangle is having G conductance and B susceptance and Y as the resultant of this G and B, and Y is the admittance. Okay, look at this impedance triangle. On the x-axis you have R, on the y-axis you have reactance, and the resultant is impedance. So these two triangles are similar. Impedance and admittance triangles are similar in nature. Only the defining terminologies are different. Okay, and total impedance is a square root of G square plus BL minus BC to the whole square. All right, the values of Y, G, B, L, BC are as I have explained earlier. So Y is equal to, if you substitute those values, you will get this. So, like we had cos phi equal to R by Z, here we have cos phi is equal to G by Y, and the phi will be equal to cos inverse G by Y. Similarly, we can have tan phi equal to B upon G, and and phi angle phi is equal to tan inverse B upon G. So this way you can calculate the angle of lead or lag. As the admittance Y of the parallel circuit is complex quantity, the admittance corresponds to the general form of the impedance Z equal to R plus JX for the series circuit will be written as Y equal to G minus JB. So similarity is there. Here we will prefer to write this prefer to write this one: y equal to g minus jb. G, like z is equal to r minus j, r plus jx. So these two, you can compare these two for better understanding. This will help you in understanding the relationship between z and y. So y is equal to g plus jb, a square root of g square plus b square at an angle of tan inverse b upon g. Now, we have an example for you for better understanding. This 1 kilo ohm of resistor, 142 millihenry of coil, and a 160 mic microfarad of capacitor are all connected in parallel across 240 volts 60 hertz supply. Calculate the impedance of the parallel RLC circuit and current drawn by the circuit. Impedance of the parallel RLC circuit. Okay, this is 240 volts 60 hertz. Now R is 1 kilo ohm, L is 142 millihenry, and C is, this is the given data in the question. Now XL is, you have to calculate XL before you calculate, B or susceptance. So XL equal to 2 pi FL, substitute the values, and this will be 53.54 ohms. XC is equal to 1 upon omega C, substitute the values, and you get 16.58 ohm. And you calculate Z impedance, which is equal to 1 upon a square root of 1 upon R. For the parallel circuit, we go like this: 1 upon 1 upon R, 1 upon XL, minus 1 upon XC. So it becomes 1 upon 1. R value of R is how much? 1 kilo ohm. So it is 1000 whole square plus 1 by 53.4 minus 1 by 16.54 to the whole square. Now if you calculate them, this comes to be 24 ohm. Z is 24 ohm. Now having calculated Z, now you can calculate Is. So Is will be equal to Vs minus Vs divided by Z, and equal to 240 by 24, and that is equal to 10 amperes. Now we have yet another example for this better understanding of parallel circuit. 50 ohm resistor, 20 millihenry coil, 5 microfarad capacitor are all connected in parallel across 50 volt 100 hertz supply. Calculate the total current drawn by the supply and the current for each branch, the total impedance of the circuit, and the phase angle also. Also construct the current and admittance triangle representing the circuit. So here is the value given: 50 hertz 100, 50 volt 100 hertz supply. R is 50 ohm, L is 20 millihenry, and C is 5 ohm. So here XL will be calculated first, which is equal to omega L, and substitute the values. You will get the value 12.6 ohm. Capacitive reactance XC is 1 upon omega C, equal to 1 by 2 pi Fc. Substitute the values, and you will get the value of 318.3 ohms. Now calculate the impedance. Impedance Z is equal to 1 upon square root of 1 by R whole square plus 1 by Xc minus 1 by XL to the whole square. Substitute the values, and after calculation you get 12.7 as the Z value of the Z. Now you can calculate IR is equal to V upon R. V upon R is the value of IR. So 50 by 50, it is 1 ampere. Current through the inductor is IL. V upon XL is the formula: 50 upon 12.6, 3.9 ampere. Current through the capacitor is V upon XC, 50 by 318.3, that is 0.16 ampere. And if you want to calculate the total current, you will have to use this formula: is equal to square root of IR square plus IL minus IC to the whole square. So calculate it: 1 square plus 3.9 minus 0.16 to the whole square. And after calculation, you get IS equal to 3.87 ampere. Now calculate conductance as said in the question. So G equal to 1 upon R, 1 by 50 is 20 millisiemens, 0.02 Siemens, that is 20 millisiemens. If you multiply it by 1000, it is converted into millisiemens. Inductive susceptance BL equal to 1 upon XL, 1 by 12.6, 0.08 Siemens, and this is nothing but 80 millisiemens. Capacitive susceptance is VC 1 upon XC, 1 by 318.3. This is 0.003 Siemens, that is 3 millisiemens. Now calculate the admittance. Admittance is Y is equal to 1 upon Z, and after substituting the value, you get 0.78 Siemens, and that is equal to 78 millisiemens. Phase angle cos phi equal to G upon Y, 20 millisiemens divided by 78 millisiemens is equal to 0.256. Now, in order to calculate the phase angle, you will have to take the inverse of this cos for this figure, and you get 75.3 degree lagging angle. So this completes the calculation. And here is the impedance triangle, current triangle and impedance triangle. Here is IC 0.16, and here is IL 3.9 ampere, and IL minus IC is having this value. Subtracting IC from IL, you get a particular value. You draw it and draw the diagonal. This gives you the value of IS. So this is the phasor diagram for that, and this is the phasor diagram of admittance triangle. So BC is 3 millihenry, BL is 80 millihenry, and the difference is 80 minus 3, that is 77 millihenry, and 20 millihenry is this. So diagonal is 78 millihenry. This is the impedance triangle. The summary is the same as we have discussed earlier, so I'm not going to repeat it. So this completes the discussion about the parallel circuit, analysis, RLC parallel circuit analysis. So I hope this was quite interesting for you to understand the ins and outs of parallel circuit. Thank you very much for being with me. Stay tuned with me for more videos.